Certain landscapes carry assumptions with them. The Appalachian Mountains are often described as ancient, worn, and tectonically quiet. A region shaped by collisions hundreds of millions of years ago and then left to erode into long ridges and gentle valleys. That description has held steady for decades, forming a kind of geological consensus about stability and inactivity. Yet, scattered across this terrain are features that challenge that assumption in subtle but unmistakable ways. Why would a region so far removed from active plate boundaries contain rocks that resemble volcanic material? Why do isolated hills rise from otherwise predictable patterns of folded sedimentary layers? And how could signs of comparatively recent deep earth activity exist in a place long considered dormant? Overlooking the central Appalachian Mountains within the Valley and Ridge province, a surprising geological feature becomes visible, hidden within the landscape. In plain view lies the remnants of an ancient volcanic system, something not typically associated with this part of the world. It is not located among the towering rugged peaks or within the intensely folded terrain such as Massanutten Mountain, nor among the higher elevations near Reddish Knob. Instead, it appears as a modest rise known as Mole Hill, situated just outside Harrisonburg. At first glance, Mole Hill does not immediately suggest anything unusual. Rising only about 200 feet or roughly 60 meters above the surrounding farmland, it lacks the dramatic profile commonly associated with volcanic features. Its slopes are gentle, its outlines subdued. Yet its presence interrupts the otherwise orderly arrangement of the valley and ridge landscape, where elongated ridges and valleys run in parallel bands shaped by folded sedimentary rock layers. This small hill does not align with that pattern. It stands apart, both visually and geologically. The surrounding terrain tells a very different story. Layers of sandstone, shale, limestone, and dolomite dominate the region, all deposited in ancient seas and later compressed, folded, and faulted during the formation of the Appalachian Mountains approximately 300 million years ago. These rocks weather in predictable ways, producing the alternating ridges and valleys that define the landscape. Harder sandstones form the ridges, while softer limestones and shales erode into valleys. It is a system shaped by long-term erosion acting on sedimentary structures. Mole Hill does not fit into that system. Its composition is igneous, meaning it formed from molten material that cooled and solidified. The rock itself is dense and fine-grained, bearing characteristics more commonly associated with volcanic regions such as oceanic islands. Its resistance to erosion is significantly greater than that of the surrounding sedimentary rocks, which explains why it remains elevated while the surrounding terrain has worn down over time. Closer examination reveals that Mole Hill is not a volcano in the conventional sense. There is no crater, no evidence of lava flows spreading across the surface, and no layered deposits of ash or pyroclastic material. Instead, it represents what geologists identify as an intrusive feature. At some point in the distant past, molten rock forced its way upward through fractures in the Earth's crust, but did not erupt onto the surface. It cooled underground, forming a solid mass. Over tens of millions of years, erosion removed the overlying material, gradually exposing this hardened core. This type of formation is often referred to as a volcanic neck or plug, though in this case the structure is somewhat more complex. The absence of surface eruption features suggests that the magma may have stalled before reaching open air, solidifying within the crust rather than building a traditional volcanic cone. What remains today is essentially the internal plumbing of a system that never fully expressed itself at the surface. Mole Hill is not an isolated anomaly. Similar formations appear along a narrow geographic corridor extending through parts of Virginia and into West Virginia. Among these are Ugly Mountain and Trimble Knob, near Monterey. Like Mole Hill, these features rise modestly above their surroundings and consist of igneous rock that contrasts sharply with the sedimentary layers around them. Their distribution is not random. Instead, they align along a subtle but consistent trend, suggesting a shared origin linked to deeper geological processes. Trimble Knob, in particular, provides additional context. Rising to an elevation of approximately 2,600 feet, or about 790 meters above sea level, it does not immediately stand out as volcanic. Its slopes are forested, and its profile blends into the surrounding terrain. Yet beneath that surface lies a composition strikingly similar to that of Mole Hill. The rock here also formed from magma that intruded into the crust and later became exposed through erosion. Radiometric dating places these formations at roughly 40 to 50 million years old. In geological terms, this is relatively recent, especially when compared to the 300 million year history of the Appalachian Mountains themselves. This timing introduces a significant inconsistency. The Appalachians are generally understood to have formed during the collision of ancient land masses, a process that ended long before these igneous features appeared. By the time Mole Hill and its counterparts formed, the region should have been tectonically quiet, far removed from the kinds of forces that generate magma. This discrepancy raises a fundamental question. If the Appalachian region was no longer experiencing the compressional forces associated with mountain building, and if it was not located near a plate boundary where subduction or rifting could produce volcanic activity, then what mechanism allowed magma to form and rise through the crust? The answer is not immediately visible at the surface. Unlike active volcanic regions, where tectonic boundaries provide clear explanations, the Appalachians offer no obvious clues. There are no subduction zones pulling one plate beneath another, no mid-ocean ridges spreading new crust, and no rift valleys tearing the land apart. Instead, the region sits within the interior of a tectonic plate, an area typically characterized by stability. Despite this apparent stability, the presence of these igneous intrusions indicates that something disrupted the equilibrium deep below. The alignment of features such as Mole Hill, Ugly Mountain, and Trimble Knob suggests that the process was not isolated but part of a broader event affecting a specific part of the crust. The consistency in age further supports this idea, pointing to a relatively brief period during which magma generation occurred. Erosion plays a crucial role in revealing these features today. At the time of their formation, the magma bodies were buried beneath thousands of feet, or roughly 1 to 2 kilometers, of overlying rock. Over millions of years, weathering and erosion gradually stripped away these layers, exposing the more resistant igneous cores. This process not only brought the formations to the surface, but also shaped their current appearance. Without erosion, these features would remain hidden, their presence detectable only through indirect means. The surrounding valleys, carved primarily from limestone and dolomite, have been particularly susceptible to erosion due to processes such as chemical weathering and dissolution. Water moving through these rocks gradually enlarges fractures, creating caves and sinkholes while lowering the overall surface. In contrast, the igneous rock of Mole Hill resists such processes, maintaining its structure even as the landscape around it changes. This differential erosion accentuates the prominence of these features, making them visible markers of deeper geological history. The distribution of these igneous bodies also intersects with broader patterns in the region's topography. The central Appalachian area where they occur is notably elevated compared to surrounding regions, forming a kind of plateau from which several major river systems originate. Tributaries feeding into larger rivers such as the Shenandoah, Potomac, James, and Cheat all trace their beginnings to this elevated terrain. While the shape of the land is influenced by surface processes, the underlying cause of this elevation may extend deeper into the earth. One proposed mechanism involves changes in the structure of the lithosphere, the rigid outer layer of the earth that includes the crust and the uppermost mantle. Beneath the Appalachians, this layer may not be as uniform as once assumed. Variations in thickness, composition, and temperature can influence how the lithosphere behaves over time. In certain conditions, parts of it can become unstable. The idea that sections of the lithosphere could detach and sink into the underlying mantle introduces a process capable of generating heat and movement where none would otherwise be expected. As denser material descends, it can create space for hotter, less dense material from deeper within the Earth to rise. This upward movement can bring temperatures high enough to partially melt rock, producing magma even in regions far removed from plate boundaries. Such a process would not necessarily produce large-scale volcanic eruptions. Instead, it might generate smaller volumes of magma that intrude into the crust along zones of weakness. These intrusions could solidify without ever reaching the surface, forming the kinds of features now observed at Mole Hill and its counterparts. The narrow geographic distribution of these features could reflect the localized nature of this process, confined to areas where the lithosphere was particularly susceptible to change. Evidence supporting this interpretation comes not only from the age and composition of the igneous rocks, but also from geophysical studies of the region. Variations in seismic wave speeds beneath the Appalachians suggest differences in temperature and composition at depth. These variations are consistent with the presence of altered or partially removed lithospheric material. While not directly observable, these signals provide indirect confirmation that the region has experienced more dynamic processes than its surface appearance might suggest. The presence of these ancient volcanic remnants challenges the long-standing perception of the Appalachians as entirely static. It introduces a layer of complexity that extends beyond the visible landscape, pointing to interactions between the crust and mantle that continued long after the mountains themselves were formed. Yet despite these insights, key aspects of the process remain unresolved. The precise timing, extent, and triggers of the underlying changes are still subjects of ongoing analysis. Even with the available evidence, the full explanation for why magma formed in this particular region at this particular time is not entirely settled. The features themselves provide clues, but they do not tell the complete story. Their modest size and subtle appearance belie the significance of the processes that created them, leaving open questions about the forces operating deep within the Earth and how they manifest at the surface. As attention continues to focus on these quiet anomalies, the Appalachian landscape reveals itself to be less predictable than once assumed. Beneath its ridges and valleys lies a record of activity that does not conform to traditional models of tectonic behavior, suggesting that even the most seemingly stable regions can harbor unexpected chapters in their geological history. The pattern formed by these scattered igneous bodies becomes more difficult to dismiss when viewed not as isolated curiosities, but as coordinated evidence of a deeper and more disruptive process. Their alignment across parts of Virginia and West Virginia, their similar composition, and their closely matched ages all point toward a single geologic episode that unfolded beneath the central Appalachian region tens of millions of years after the mountains themselves had already taken shape. This timing is critical because it places the event well outside the known periods of continental collision that originally built the Appalachians, and far removed from any active plate boundary where magma generation would normally be expected. By approximately 50 million years ago, the Appalachian Mountains had already undergone extensive erosion. Once comparable in scale to major modern mountain belts, they had been worn down significantly, their peaks reduced, and their valleys broadened. The tectonic compression that created them had long ceased. In most models of Earth dynamics, such a setting should not produce molten rock rising through the crust. Yet the evidence preserved in Mole Hill, Trimble Knob, and similar formations indicates that magma was indeed generated and that it moved upward through the lithosphere before cooling and solidifying below the surface. The explanation that has gained the most traction centers on a process that does not leave obvious marks at the surface, but instead operates deep within the Earth. The lithosphere beneath a continent is not permanently fixed in place. Over long periods of time, it can undergo structural changes driven by variations in temperature, density, and composition. In certain circumstances, the lower portion of this layer can become gravitationally unstable. When that happens, it may detach and sink into the underlying mantle, a process known as lithospheric delamination. This process introduces a chain of consequences that can extend upward into the crust. As the denser portion of the lithosphere descends, it creates a void that allows hotter mantle material to rise in its place. This upwelling is not necessarily explosive, nor does it always result in widespread volcanism. However, it can increase temperatures enough to partially melt the surrounding rock. The resulting magma, less dense than the solid material around it, begins to move upward through fractures and zones of weakness within the crust. In the case of the Central Appalachians, the volume of magma generated appears to have been relatively limited. There is no evidence of extensive lava flows or widespread volcanic deposits. Instead, the magma likely intruded into the crust in localized areas, forming pockets and column-like structures that cooled underground. These intrusions would have remained hidden beneath layers of sedimentary rock, indistinguishable from the surrounding material at the surface for millions of years. The key to their eventual visibility lies in the long-term action of erosion. Over tens of millions of years, water, wind, and chemical processes gradually removed the overlying rocks. In some areas, this removal amounted to several thousand feet or more than 1 kilometer of material. As the softer sedimentary rocks were worn away, the more resistant igneous bodies were left behind, standing slightly higher than their surroundings. What is visible today in features like Mole Hill is not the original volcanic system, but rather the internal core that once lay deep beneath it. This interpretation helps resolve one of the central questions surrounding these formations: why they appear volcanic in composition, but lack the defining characteristics of surface volcanoes. They are not remnants of eruptive cones or lava fields, but instead represent the preserved interiors of a system that never fully reached the surface. Their present appearance is the result of exposure, not construction. The narrow geographic distribution of these features also becomes more understandable within this framework. Lithospheric delamination does not occur uniformly across an entire continent. It tends to affect specific regions where conditions favor instability, such as variations in crustal thickness or the presence of older structural weaknesses. The corridor stretching through parts of Virginia and West Virginia may represent one such zone, where the lower lithosphere detached and allowed mantle material to rise. This process may also be linked to broader changes in the elevation of the region. The Central Appalachians stand higher than surrounding areas, forming a plateau-like zone from which several river systems originate. While erosion-resistant rock plays a role in maintaining this elevation, deeper factors may also be involved. The removal of dense lithospheric material and its replacement by lighter mantle could contribute to a gradual uplift of the land above. This uplift would not be sudden or dramatic, but it could influence drainage patterns and the long-term evolution of the landscape. Seismic data collected from the region adds another layer of support to this interpretation. Waves generated by earthquakes travel at different speeds, depending on the properties of the material they pass through. Beneath the Central Appalachians, variations in these speeds suggest that the structure of the lithosphere is not uniform. Some areas appear to have been altered or thinned, consistent with the idea that part of the lithosphere was removed or modified in the past. While this evidence is indirect, it aligns with the observed distribution and composition of the igneous intrusions. Despite these insights, the exact sequence of events remains only partially resolved. The timing of the delamination, the amount of material involved, and the duration of magma generation are still subjects of ongoing study. What is clear is that the presence of these igneous bodies cannot be explained by surface processes alone. They point to a deeper origin, one that involves the interaction between the crust and the mantle in ways that are not immediately visible. The realization that such processes occurred beneath the Appalachian region challenges long-standing assumptions about its geological history. It suggests that the area was not entirely dormant after the end of mountain building events, but instead experienced a later phase of internal restructuring. This phase did not produce towering volcanoes or widespread lava flows, but it left behind subtle yet persistent evidence in the form of these resistant igneous features. Near the end of this line of evidence, the underlying explanation becomes clearer. These mysterious ancient volcanoes are not volcanoes in the conventional sense at all. They are the exposed roots of a hidden event that unfolded deep underground, long after the mountains above had already formed. Their existence reflects a period when the foundation of the continent itself was undergoing change, allowing heat and material from the mantle to rise closer to the surface. The magma that formed during this period did not erupt widely, but it left behind solid traces that, once uncovered by erosion, appear as isolated volcanic-like hills scattered across the landscape. These quiet landforms, easily overlooked and often mistaken for ordinary hills, serve as surface indicators of processes that reshape the region from below. They confirm that stability at the surface does not always reflect inactivity at depth, and that even the most established geological interpretations can shift when new evidence is considered in full context. If this breakdown gave you a clearer picture of how something so subtle can reveal such a deep earth process, consider supporting the content. Like, share, subscribe, and tap that hype icon to help this reach a wider audience.